So our next speaker is Hugh of University of Warwick. He's a principal engineer in the Cyber Security Centre. Hugh is a chartered engineer, a fellow of the IET, and holds the CISSP credential issued by the ISC. He specialises in security of cyber physical systems and has written a number of guideline documents relating to security of the built environment and the control systems used within them. The title of Hugh's talk is Cyber Security in the Internet of Things and Complex Cyber Physical Systems.
Thank you. So, we've been talking about all sorts of testing and verification challenges. In the physical world, we understand what failure is. This is BP's Deepwater Horizon. It's pretty obvious when it's failed. Smoke, flames, large damage claims. Something that's actually very easy to deal with. These sort of events don't happen too often. Why? Because this is physical engineering. We understand that quite well. We've been doing it forever. And the standards we work to are generally quite good. Sadly, when we move into the cyber world, life is not quite so clear. The first challenge we have is what do we mean by security? Security is bandied around quite glibly in terms of IT systems. What it generally means is passwords and encryption. I'd like to disabuse you of that, because in cyber physical systems, security is actually about the reliability of that system, avoiding the smoke and the flames. Last year, the Engineering Council, for the first time ever, issued some guidance on security for engineers. I was part of the team drafting that, and it was quite an interesting set of discussions we had, because a number of the people in the room were actually from the safety community. And we had some debates about this definition. What's quite key is the use of the words threat or harm. My contention is an awful lot of the safety problems are the same as the security problems. The only difference is the security issues are caused by malicious or ignorant behaviour usually. So actually, if as an engineering community we can start working together and thinking both about the threats to the systems as well as the harm that can be generated through hazards, we actually might start to tackle many of the security problems that we talk about today. The second challenge we have is what do we mean by cyber security? I hear an awful lot of people talking about it as being purely a digital security problem. Again, I'd like to disabuse you of that. I work on some very complex systems. They involve both analog and digital components. The analog components are often wireless, or the electronic components that connect our systems together. Again, we also think about cybersecurity as being purely technology. Oh, if it only were. 80% of the problems I deal with around national infrastructure are due to people, process and physical. And they are the toughest ones to solve. I know we're talking a lot about testing today, but actually it's these other issues that can be just as lethal, just as fatal to our systems. For example, how often do we actually think about the physical connections to our IT systems, the location of them, the ease with which they can actually be damaged or flooded? All of those have quite significant security and resilience issues. I'd also like to introduce you to an engineering view of what security is, or cybersecurity is. Now, the information assurance community have talked for years about the CIA triad. That's the top bit. If you're dealing with administrative systems, processing checks, claims, etc., that's fine. Because actually what you're generally thinking about are two things: confidentiality and integrity. The confidentiality being you don't want unauthorized people to see the contents of those files to get to say personal data. The integrity being we actually want to know the data we're processing is the correct data. Availability comes a long way behind. It's usually third in the queue. Why? Because actually if your claims processing system goes down, you just wait a day or two. As we know from banking failures, if check clearing or cash transfer systems go down, we can actually survive for 10 days without having catastrophic problems. You can't say the same about cyber physical systems. If the energy supply network goes down for more than a short period, the UK will grind to a halt. If you doubt that, look at what happened up in Lancaster when a substation got flooded. We converted a 20th century city back to the dark ages. ATMs didn't work, lifts didn't work, and within 12 hours the telecoms didn't work. Looking at the other elements on here, I'd like to take you through a few. Safety. My contention is you cannot have safety if a system is insecure, because fundamentally, if it's insecure, I can make it do bad things. When we're talking about things like autonomous vehicles, that is going to happen. We've seen the first hack on a Jeep. That's just the tip of the iceberg. I work with some really talented engineers who could make that look like a picnic. Resilience. That's the ability to deal with a degraded system and recover quickly. How often do we think about that? On CNI type systems, on infrastructure systems, the answer generally isn't turn off and reboot. We can get away with that on a desktop system. You can't get away with it on a cyber physical system. Or generally, you can't get away with it without some serious consequences. Utility. We talk about digital systems having relatively short life cycles. I do a lot of work with the construction industry around the built environment. We're looking at building assets that will have lifetimes of 50 to 100 years. The IT technology that's going into them, if it lasts more than a decade, we'll be lucky. So what format are we storing our data in? What type of technology are we using? From personal experience, I know that trying to access a file I wrote containing my dissertation for my MBA is now impossible. It was written in 1995 using a Lotus word processor on Windows 98. It's completely inaccessible. There is no tool today that will access that file easily. I have to rebuild the system to do that. It's a good job I have a paper copy. But if we're looking at the designs of our future engineering systems, our future buildings, and they're all purely digital, how will we access them in 20 or 30 years, let alone in a century? Authenticity. This is a gem. We're moving over to increasingly wireless-based solutions. I started my life as a communications engineer. I know that if you're in that space, it's really difficult to verify where the signal came from. So how do we know our data is authentic? Because generally we're not designing that into our solutions. And then the pair that go top and bottom. We understand confidentiality generally, but do we understand possession? Well, possession is what Stuxnet was all about. It was a brilliant design that fooled the operator. So looking at complex cyber-physical systems, they are becoming increasingly complex. No longer are they just in the box. What we're seeing is use of cloud. Now what do we mean by cloud? It means you're processing your data on somebody else's system at a location they choose to specify and can vary at any instant in time. The AWS example that was recently given is a classic cloud problem. But how many people are actually thinking about that? If that was a control system or an intelligent transport system that's relayed its data back to the cloud to process, what would the consequence be with that sort of AWS outage? This is a modern building system. This is the sort of system I have to worry about quite routinely. Every component on there includes technology. At the bottom end, it's relatively crude. It can be PLCs, it can be circuit boards. But as we move up that stack, we're moving into commercial operating systems, quite often Microsoft. We have internet connections. We have operators who will sit on a control workstation accessing their Gmail or Yahoo accounts, having no concern about what they're actually downloading. And two observations I'd make about that is, why on earth do you want to connect a control system to the internet? It doesn't need to be. And secondly, if you're looking at a Microsoft operating system, how on earth can we verify that it operates properly? It's no longer code that you can test. It is just millions and millions of lines of code. And as we know from Patch Tuesday, it's not without its bugs or those features. So why does security matter? This is an example from the United States. The jail is where Miami keeps some of its worst offenders, drug dealers, murderers, as it were, the scum of society. This incident involved prison doors opening in the high security wing. The glitch, as it's so called, has actually occurred in other prisons. What's interesting is the control system is actually a Windows-based touchscreen monitor. And when you look at the system diagram that the supplier of that system quite freely publishes on the internet, there are all sorts of interesting components on there. An ADSL router, Wi-Fi and Bluetooth access to components. Why? This is a high security system for deployment in prisons, not the sort of environment you'd want to trust wireless access or any connectivity to the internet. Google. We would hope that they would be really good at security. Well, they generally are, until it comes to their building systems, or so we discovered in 2013 in Australia. A white hat hacker discovered this floor plan. What he first found was a login screen that he thought, that looks really familiar. It was an Niagara AX building management system. It still had the default username and admin password set. Admin and admin. Had he accessed this screen maliciously, what he could have done is shut down that entire building. Not really the sort of thing you ought to hear from one of the leading technology companies. There's brief mention in one of the other talks about the Mirai botnet. Now what's significant about this is actually these sort of nets are really easy to create. We can find them using a specialist search tool called Shodan. The example we have here, the Mirai botnet, was basically home CCTV cameras. They're IP based and they have a web server built in. It's not properly configured. It's fundamentally insecure. But I have other examples that particular search engine can find. Solar farms in Germany, where we can find the controller. A little bit of due diligence on the internet tells us what the username and password is that the maintainers use. The password is all of 3 characters. Even if we didn't find it, we could crack that in seconds, because the sort of box we're dealing with doesn't have any way of preventing brute force attacks. I see some rays of hope. D-Link in the United States is being sued by the Federal Trade Commission, I think partly as a result of the Mirai botnet. This is a major step forward. If we can see manufacturers of components like that having to take responsibility for their components and having to start to secure them, we might drive the standards up steadily. However, some organisations still haven't learned. Sony's been hacked twice in a major fashion, and yet it's still deploying, or was still deploying, cameras with basic faults. From a recent check on this, I believe that their solution to that is they've now sold that division. But that's not fixing the problem, it's just transferring the risk. Then we get to inappropriate information sharing. So how many of our IoT devices are actually compromising our personal data? Do we know where it goes? Do people understand what the Fitbit on their wrist is doing? Well, the fact if they're wearing it 24 hours a day, they're communicating an awful lot of information back to the US about their personal behaviour. As I discovered when I spoke to a young female colleague, she had no concept about what data is being communicated, or the fact that actually wearing it 24 hours a day might not be a good move. In the built environment where I work, we have very sophisticated digital models. This one is of the underground infrastructure near London Station. What's horrifying about this is the infrastructure we're showing here is not owned by the people that produced this map, this visualization. And some of it is actually critical national infrastructure. Then there's the Internet of Things. It's been touched on already. So what is it? It's not actually an Internet of Things, it's an interconnection of things. And that's quite an important difference, because many of these devices aren't actually connecting directly to the internet, they're connecting to some other device first. So we have insecurity both at the device level and the connections beyond it. We're seeing IoT straying into control systems, which is going to be a major cause of problems in future, because these are cheap commodity devices being tucked into quite sophisticated processing systems. Who's architecting the security of these, and who's then testing it? It's touching all aspects of our lives. So we now have the car being regarded as an Internet of Things or IoT device because it's becoming a connected vehicle. Should we really be seeing 2 tons of steel or steel and plastic being internet connected with potential connectivity directly through to the control systems due to the way we actually engineer the head-end unit that provides the entertainment? Would hope not. But that's where we are today. The developing architectures are still quite crude. They're getting better. And people like the GSMA are doing work. But still we're seeing Bluetooth, Wi-Fi and other protocols being used with no security protection, no security architecture. And frankly, if you're using wireless, you're in my area. I can jam or I can interfere. There are a number of ways of addressing the challenges. We need to establish trust in an untrustworthy world. We also need to start engineering these systems. There are other things called the 20 critical controls that I'll point you out. This is actually good engineering practice, it's not security. And there are plenty of standards and guidance out there, if only we'd apply them. Am I out of time yet?
Yeah.
So I think testing and verification has a critical role. And I'd really like to see more of it applied in a security context rather than purely about the functionality. The web interfaces. Frankly, we can do an awful lot to test those. So if we're deploying IoT devices with a web interface, let's sort it out. The wireless connections. We understand security of those, if only we'd apply it. And in terms of installation and setup, why aren't we delivering things that are secure by default, that come out of the box secure, and then you can turn off the security features if you really don't want them? Thank you. Any questions?
Thank you very much. Thank you, Hugh. Do we have any questions for Hugh? I know the coffee's ready, because I put the kettle on a couple of minutes ago. So
Hugh, Jeremy Bennett, Embercosm. I think you talk a lot of interesting things, but I think some of it rather doesn't address the very bottom end, the extremely resource constrained. Your smart card that is getting its entire power to do all its security from an induction coil, what it can hold in a capacitor. And sometimes it's wishful thinking to say, I want high-level secure networks. What's your thinking about how you secure when you actually have got very resource-constrained environments?
So I think our first challenge is defining what we mean by security in those circumstances. If we're looking at a bank card or an access control card, yes, we need to have those features built in. If we're looking at a sensor collecting data in the field, be it an agricultural field or industrial, what do we actually want? We don't necessarily need encryption on that. What I want to know is where is the device, and is it my device, and is it communicating the right data? So in those circumstances, encryption actually is misleading. All you're doing is protecting the pipe. You're not telling me that the data flowing through the pipe is the right data. In terms of resource constraints, well, some of this comes down to what technology do we actually need to field? The answer often is lots more computing power, lots more digital. But we've been doing an awful lot of this in the past with analog components that were really effective. So why are we pushing, for example, internet technologies, Ethernet, out right into the field? Serial communications can be made secure. We don't need the bandwidth then. So it's all about, I think, engineering design, rather than just saying, we've got a chipset, let's deploy it.
Okay. And last question from Andy.
So on that last point, doesn't it all come down to legislation eventually? I mean, the reason no one's doing it is because it's cheaper not to do it, and you don't get any backlash when it goes wrong. So this is not the industry's responsibility. They've got shareholders who will be affected by this. Until there's a pushback to actually do this correctly, it's not going to happen.
So there's a couple of areas of pushback. Firstly, the US FTC, as it were, piling into D-Link. Delighted to see that, because frankly, if you as a company like D-Link are producing an item that is so fundamentally weak in its security, you have a product liability issue to address. Now they're trying to wriggle like mad in California, but at least the courts out there understand technology. So there's a good chance if the FTC press their case, we'll get a conviction. And that will be the first time in some ways that software engineering has actually been taken to court and held up to the standards that hardware engineering already is. The second development in the UK is there's a thing called PAS 754, which is about software trustworthiness. That's being converted at present into a British standard, which will then be passed up to ISO potentially for international use. Once that actually gets published and accepted, again we will have a benchmark for software engineering. Software will stop being an art, which is where it is today, and it will turn into an engineering discipline. It's about time we achieved that, because frankly some of the code I see written and published is just purely negligent. It's incompetent, some of the stuff. You just have to look at a number of the, as it were, open source cases that have been out there and think these are supposed to be professional programmers who are doing this, you know, as a gift to society. But the code they're writing is fundamentally wrong. Heartbleed demonstrated that with OpenSSL. And frankly, it makes you cry when you look at that code. The OpenBSD team ripped it apart. And some of the stuff they wrote about it, you just think, how on earth are people getting away with publishing that? But equally, how are the industrial control system manufacturers, I don't want to name them particularly, but you can go out and find their names, all the major players have incorporated that software in their products. And I'll wager none of them had actually opened the code up and checked it. To me, again, that is negligence, it's professional negligence. Because if you as a product supplier are not checking your components, your code, who is?
Last question.
Hugh, this is a very quick comment. Your comment about open source can't go without saying. You could see it was negligent. Don't assume because something's closed source and you can't see the source code that it's not negligent.
Oh, absolutely.
On that bombshell. Okay. So we are going to break the coffee. Thank you very much, Hugh. Just before you go off, you know, after the break, we've got a formal verification talk from OneSpin, and then our keynote speaker at the end of the day is John Colley, who's going to pull everything together because John is talking about safety, security, hardware and software. So everything comes together at the end of the day as if it was planned that way. It's fantastic. Thank you. Thanks, Thank you.